Alright, a lot of math is all about patterns and identifying patterns and using patterns to make things easier for us. And so we're going to talk about sequences and series. So suppose you've been offered two summer jobs. One where you get paid $70 the first day, $71 the next, $72, $73. You're getting a raise every single day. And so you can sort of notice the pattern where you start at 70 and increase by $1 per day. Suppose that was a dollar sign. And then the next one is you start, and whatever day it is, this is 1. Day 2 you get 4 cents, day 3 you get 9 cents, day 4 you get 16 cents. Compared to option A, this looks pretty sad. Walking away from a whole day's work, just making a penny. But we're going to see later that this would actually be really pretty sweet in the end. But so you start at 1 cent, but then think of it as this is 1 squared, 2 squared, 3 squared, 4 squared. So you have to start noticing 1, 4, 9, 16. You have to recognize those as the pattern. So it's whatever day it is, number of day squared divided by 100, because we're getting it to pennies. So one thing you can do with sequences is that you can graph them. And so if we started at, and we made our n, the number of term we have on this side, 1, 2, 3, 4, 5, and we can have the dollars made on this side. So suppose this is 70. The first term 1, 2, 3, 4, 5, and suppose this is 75 up here. You get 71, 72, 73, 74. And so we don't connect it with a line because there's nothing in between. Sequences and sequences deal with just the integers, and so that's what we want to leave it as. They can also look like a curve though, and so that's what I wanted to represent here. 2, 3, 4, 5. And so let's make 0.16. Let's make that divided into thirds. 0.05, 0.10, and 0.15. So first term down here, 1 cent. Then we have 4 cents. And then we have 9 cents. 16. 25 is going to be way up here. So you see that it's got the parabola shape to it because it's being squared. Another way we can represent sequences is by using an nth term, so that we don't, so we can just plug in 5 and find the 5th term, or we can plug in 10 and find the 10th term. So we're going to write a rule, and so what we noticed is that the other one started at 70, and then we added 1 each time. So it's kind of like a line, right? Where this is the y-intercept back here. And so think of it as really, if we did 70 plus whatever n is, we'd be 1 too high. And so we actually want to do 69 plus whatever term we have, 69 plus n. So we're going to use this a sub n to represent our nth term. And all it is notation for it. And so if you plug in 1, you get the first term, so 69 plus 1 is 70. And then, if you want to think of this as 1n, we're going to call these arithmetic sequences. I'm going to talk more in depth about that in the next one. But this is our nth term equation. Option B. Remember how we talked about how it was 1 squared, 2 squared, 3 squared, 4 squared. And so that's whatever term you are, so whatever n is, squared, and then divided by 100 is what we said, or times 100th. And so our a sub n term is n squared over 100. So a sequence, all a sequence is a pattern of numbers. And each number is called a term, and you can use notation like a sub 1 to represent the first term, a sub 2 to represent the second term, or a sub n to represent the nth term. Sequences can end, meaning they're finite, or they could be infinite, meaning they don't have an end. Nothing new there. And we can also have a series where we adding a sequence. And so, for example, if we added up all of those options, all of those numbers we were having in the other one, so 70 plus 71, so the sum of the first 2 days of our work, plus 73, and so on. So, if we stopped working after 40 days, that would be a finite sequence, or if we never stopped working, that would be an infinite sequence. So a series can be represented with this notation called sigma notation, and that's what we're going to talk about next.